So what I want to talk about today is the tidyverse. And the goal of the tidyverse is not just individual R packages, but kind of an ecosystem of R packages that work together to make data analysis as easy and as fun and as seamless as possible. And to me, when you're thinking about doing data science, there really are these 7 main components. So the first thing you always have to do is get your data from whatever crazy format it's currently stored in into your analysis environment of choice. You've got to import it in from disk, from a database, from the web, and get it into R. Once you've done that, I think it's a really good idea to tidy your data, to store it in a consistent format. We'll talk about this idea kind of again and again throughout this talk, but this idea of sharing structure, of constructing some uniform object that you can operate with in the same way for many different tasks is a really, really powerful idea. Once you've done that, once you've tidied it, you'll often do some transformation. That's things like adding new variables that are functions of existing variables, creating summaries, collapsing your data down, or maybe just rearranging the rows or picking out from hundreds of variables just a handful that you're interested in. Once you've done that, in my opinion, there really are 2 main engines of knowledge discovery: visualization and modeling. Now, visualizations are fundamentally a human activity, and they're great because they can surprise you. They can show you something that you did not anticipate. Visualizations are also really great at helping you make those sort of vague, ill-formed questions in your head into precise questions that can be answered quantitatively. So visualizations are great because they are fundamentally a human activity. But that's also their downfall, because a human has to look at every visualization, and that means they fundamentally do not scale. As you get more variables, as you get more observations, you simply cannot look at every possible visualization. So to me, the complementary tool to visualization is modeling. And I think of modeling as very broadly, but basically whenever you've got a precise question that you can answer with a simple algorithm or some summary statistics, I think of that as a model. That's statistical modeling, that's machine learning, that's deep learning, that's data mining. And this is fundamentally a computational tool, right? This is something that computers do. And again, this has its advantages. It scales much better, and even if it doesn't scale that well, you can just throw more and more computers at the problem, and that's much, much easier than throwing more brains at a problem. But every model makes assumptions, and a model by its very nature cannot question those assumptions. So that means at some fundamental level, a model cannot surprise you. So you've got visualizations, a human activity. They can surprise you, but they don't scale. Models are fundamentally computational activity that can't surprise you, but do scale. So any real analysis is going to involve you circling through these things many, many, many times. Now, at some point, you're going to have circled through these enough times, you're going to come to some conclusions, and we're going to get to one of the most important parts of the data science process, which I am not going to talk about at all tonight. And that is the process of communication. It doesn't matter how amazingly wonderful your analysis is unless you can explain it to someone else in a way that they can take it. So I'm not going to talk about that tonight, but I'm going to talk about pretty much all of these other pieces. And I'm also going to talk a little bit about programming, because this is sort of the sea in which all of these things live. You cannot do modern data analysis without a computer, and to do, in my opinion, high-quality data science, you must be able to program. Now, when we look at this diagram, I think it's very natural to kind of focus on those verbs. Like we think, like, what are these important tools? But as Hal Abelson says, it's not just those individual tools, it's how they fit together. In other words, I think when you look at this diagram, you kind of see these words, these big picture: import, tidy, transform, visualize, model. They really jump out at you. But equally, what you have to think about is the connections. Because if those connections are smooth and seamless, you can iterate very, very quickly. And I think iteration is so important because every good data analysis starts off as a bad data analysis. There is no other place to start except with something bad, and then to iterate again and again and again until you get something good. And so what I'm going to talk about today is basically the idea of the tidyverse is to really think about, well, what makes what makes these tools fit together in a way that they just seem natural, that you don't have to think about transitioning between these different steps. Things just happen naturally without you really having to pay a lot of attention. And so what I'm going to talk about today, I've kind of called it this manifesto, which is a little highfalutin, but 4 kind of basic ideas that tie together all of these packages in the tidyverse, packages that help you solve all of these different parts of the data science process. So the 4 ideas are, first of all, you want to share data structures. You want to solve complex problems by composing simple pieces. You should embrace functional programming. And then finally, I think you really need to recognize and embrace the fact that all of these tools are used by humans. And I think that that's something that's really, really important. We'll come back to it. So these ideas tie together the packages in the tidyverse, but I hope that they help you kind of frame your own analyses too. These are ideas that if you embrace will make all of your analyses a little bit easier. And the first one is this idea that you want to share data structures. And I think the most important data structure in statistics and data science is this idea of tidy data. And basically there are 2 key principles behind tidy data. The first is you take each data set you have and you put it in a data frame. And the second idea is you make sure that every variable is represented as a column, or every column is a variable. And when you do that, you'll naturally find then that each row represents a case. So that's a little bit abstract. Let's make it concrete. So here's a messy data set. And the thing about messy data sets is they all are messy in slightly different ways. So this is some data about tuberculosis collected by the World Health Organization. And what I'm going to do is I'm going to give you guys a challenge. What I want you to do is try and figure out what are the variables in this data set. So I told you it's World Health, it's data collected by the World Health Organization about tuberculosis, and I'm going to give you 3 hints. F stands for female, U stands for unknown, and 1524 stands for 15 to 24. So what I want you to do is take 1 minute, starting now, discuss it with your neighbor. What are the variables in this data set? Okay. So what is a variable in this data set that is easy to spot? Does anyone want to volunteer one? The easiest, year, right? Year is a variable. Did anyone guess what this variable was? ISO country code. Some of you guessed correctly that this is the ISO 2-letter abbreviation for a country, and AD as Andorra. So guessing this from that context is a little bit hard, but I told you this is data from the World Health Organization, right? And you expect if the World Health Organization is going to be collecting data, there's probably going to be something about country somewhere in there. So we've got 2 variables that are already in columns. What other variables do we have here? Age range. We've got an age range and the gender. And where are those variables? They're kind of like spread across the column headings. Right? So we've got 2 variables in columns. We've got 2 variables in the row, in the column headers. Are there any other variables in this data set? Yeah, what do these represent? The number of cases. Right? So we've got 5 variables here stored in 3 different ways. In columns, in row headers, and then in the cells themselves. So as you can imagine, this inconsistency, the fact that we've stored variables in 3 different ways, is going to make this data very challenging to work with. And basically every data set that's messy has this problem. Instead of storing the variables consistently in the columns, they're going to be stored in all sorts of different ways. So what we can do is we can take that data and we can make it tidy. And in a tidy data, basically each column is now a variable. So we have a column for country, a column for year, a column for sex, a column for age, and a column for the number of cases. So every tidy data set is uniform in this sense. And so to kind of paraphrase Tolstoy, tidy data sets are all alike, but every messy data set is messy in a different way. So this idea, the idea here is that if you store things in a consistent way, they're much easier to work with, right? But every problem, if you always, the first step you do is put your data into this tidy structure, everything is going to be much easier in the subsequent steps because you don't need to fight the different structure, new structure, every time you do a data analysis. Now, I'd say in data science, probably like 80% of what you deal with can be kind of shoehorned with not too much effort into a tidy data frame. There are lots of other things, of course, that are really important. You've got matrices, and there's a really nice blog post by Jeff Leake about why there's lots of types of data that he works with, particularly in bioinformatics, that are not naturally represented as data frames, but are more naturally represented as matrices. We've got things like that are used to build up the data frames, like strings and dates and all sorts of other vectors. We've got hierarchical things like XML and all sorts of other bits and pieces. But I argue, like, even if you can't use a tidy data frame, you should still try and be consistent. You want to pick a useful data structure and stick with it, learn it inside out, and then apply it in many, many, many new problems. Now, there's another challenging case, and what is if you have a mix? What if you have some things that kind of seem to be naturally observations or variables, and some things that are a little bit different? And I think a really good example of this is doing cross-validation, where basically you're going to have lots of models fit to lots of data sets that have been selected randomly. And so when you do cross-validation, you're going to start by taking your data frame, you'll split it up into a test data set and a training data set, you'll fit a model to the training data set, and then you'll get the predictions of that model to that test data set, and then you'll compute some kind of measure of quality. How well did that model do at predicting that data set, like the root mean squared error? Well, it turns out this still kind of fits into this tidy data framework if you extend this idea to think about list columns. So I'm not going to talk about this too much today, but I think this is a really, really powerful idea. So here we have a data frame. We've got a column that is a list of resamples that represent our training data, resamples are our test data. We've got some indicator that just gives us an ID for each row, each model. We've got the model, and then we've got the root mean squared error of that model that was fit to the training data set applied to the test data set. This is a really powerful idea because in our data frames don't just have to represent these low-level things, these vectors like numbers, but they can also represent more complicated things like a resample of a data set or a linear model. But one problem, one reason it's difficult to work with these things in base R is because of the way that data frames work. And so I'm going to give you guys another little challenge. I'm going to give you a minute, and what I want you to do is take this code and I want you to run it. I don't want you to run it in an R console, I want you to run it in your head and predict what the output is going to be. Again, 1 minute starting now, talk it over with your neighbors. Okay, so the first thing, hopefully you noticed, I'm creating a data frame with a variable called xyz, and then I try and extract a variable called x. What happens? You get an error? Incorrect. Actually, what happens is R has this helpful behavior where it is going to pick the variable that has a common prefix. It starts with the letter x. So it's going to pick the variable called xyz. So it's going to pick this variable, and what type of variable is that going to be? So some of you have said characters, and some of you have said factors. You are both correct, depending on the value of the global strings as factors option. But in this case, I've set it to the default, so I get a factor back. So there are two surprises here, right? First of all, we have this partial matching, so we get a name that's longer than the name we gave it. And then second of all, R has helpfully converted our character vector into a factor for us. And to explain why R does this, I think it's really useful to understand kind of two tensions. The first tension is the tension between interactive data analysis and programming. And I think when you compare R to other programming language, R is pretty strange. And that's because it's not just a programming language. It is also this environment for interactive data analysis. And there are things you want to do when you're analyzing data interactively that are not so great when you're using R as a programming language and vice versa. And so base R kind of falls fairly heavily on the interactive side of things. And so in this case, both of these things it's tried to do were helpful at the time they were written. So they were helpful because instead of typing out these very, very long variable names, you could just type a unique prefix. And because at the time that, well, R didn't have proper character vectors for a long time, and factors were much, much, much easier to work with. So these are things that were designed, 10 or 15 years ago to be helpful. And at the time, they were helpful. And the other reason, the reason to understand why those behaviors still exist is the second tension. This tension between being conservative and backward compatible and being utopian and making things work by breaking things. So base R is pretty conservative, right? The goal of base R is you can take base R code from 10 or 15 years ago and you can run it pretty much unchanged today. Now that's not true of R packages, but by and large, if you just take pure R code, code that works 10 years ago will work today. And that is a really, really strong feature of base R. But the downside of that, though, is, right, if someone made a mistake 15 years ago, it's very hard to escape from that mistake. So kind of the other side, the other perspective, instead of being conservative, you can be utopian. And right, if you're a utopian, that basically means if things aren't perfect, you're like, let's burn it all down and start again from scratch. Now, obviously, I'm much more on this, on the utopian side of things. So these aren't it's not like one side is good and the other side is bad, right? But there's different tensions. Being conservative means your code keeps working year after year after year, but it also means that you're trapped into mistakes you made a long time ago. Being utopian means you're free to fix those mistakes, but equally it means that things are always changing. Things are constantly getting better, which can be frustrating when you're just trying to do something that used to work. So one of the utopian things I've done is to create this idea, this thing called a Tibbal. So Tibbals are data frames that are lazy and surly. Now, that doesn't sound like two good features, but it turns out I think those things are quite useful. So the first thing is they're lazy because they don't try and convert anything. If you create a Tibbal with this value A, you're going to get a character vector back. It's never going to turn it into a factor, trying to be helpful behind your back. It does some stuff with subsetting, so if you use the single square bracket in base R, if you select a single variable, it will give you a vector back. If you select multiple variables, it will give you a data frame back. That's one of these things that turns out to be pretty nice when you're programming interactively, when you're doing an interactive data analysis, but is a huge pain when you start to write functions. And then finally, they're surly, because if you try and extract a variable that does not exist, you get a warning. And the other thing that Tibbals do, kind of bringing me back to the original point, is they work better with list columns. So formally, the definition of a data frame in R is a list of vectors where each vector is the same length. And a list is a vector, so that means a data frame can contain lists of things. But if you try and create a data frame with a list column in base R, you'll get this weird error. Because basically, rather than interpreting the element of the list as elements going down the rows like all the other vectors, it interprets them as columns. You can kind of work around that by putting the identity operator around it, which works. You don't get a fantastic print method. It's hard to tell here that this is a vector containing the number 1 and 2, not the string containing the number 1, comma, space, and then the number 2. With Tibbals, it's really easy, and the other advantage of a Tibbal is Tibbals try and tell you a bit more information about the structure. When you print a Tibbal, as you might have noticed earlier when we looked at this world health data, it also tells you the type of every single column. So this is really, really useful because you can check, is this what I expect it to be? Okay, so that's the idea. The first idea is you want to share data structures as much as possible. You want to kind of find the common set of principal components that you use in many, many, many analyses. You want to make those explicit, and you want to think about, well, how do I get whatever messy data I'm in into this consistent form? And if you do that, your life becomes much, much easier, because once everything's in that consistent form, you can use a set of consistent tools with it. The next thing I want to talk about is a very general strategy for solving complex problems. And that is a really powerful way of solving complex problems is to combine simple, uniform pieces. And we see this strategy in real life, I think, in two really powerful places. The first is the standardized shipping container. Right? It does not matter what is inside that crate. It could be a sports car, it could be full of teddy bears, right? It does not matter. From the outside, it has this very simple, uniform interface. You can stack these together very, very easily without worrying about what's on the inside. The other example is Lego. You can take a Lego block. Each Lego block by itself is very, very simple, right? You can pick up a Lego block and pretty easily understand, like, what does this thing do? But when you start combining them together, you are not really limited in your freedom. You can create many new different things that the original deviser of that block never imagined. So how does this play out in R? Well, I think one of the things that has really shaped my thinking recently is this idea of the pipe. How many of you have seen the pipe before? So this is not a new idea by any means. This is an idea from Unix has pipes. There's many, many other similar things in other programming languages. But the idea in R, I'm going to illustrate by telling you a little story about a bunny called Fufu. So little bunny Fufu, if I was going to describe, now that I think of it, I'm not entirely sure what the gender of little bunny Fufu is, but what this bunny does, well, they hop through a forest, and they scoop up a field mouse, and then they bop it on the head. Right, so here I describe that sequence of operations as you might in a computer language using function calls. And this is a little unnatural, right? Because we've got to read from the inside out, from right to left, and then the arguments of these functions end up spread quite far apart. And what the pipe basically does is it allows us to rewrite this, which from the computer's point of view is great because functions are simple, they're easily understood in isolation, we can compose them together in easily understandable ways, but they're not great for humans. The pipe allows us to transform this thing that's great for computers into something that's great for humans because now we can read this as basically a sequence of imperative operations. Little bunny Fufu hops through the forest, then scoops up a field mouse, and then bops it on the head. So let's bring this back to R. And I think one of the things that's really neat about the pipe is that the package basically needs no understanding of the pipe for it to work. It takes this really powerful idea from computer science, simple functions that are composed together, and allows us to express this idea in a way that humans can easily understand. But there's a bit of a problem. So to illustrate what goes wrong when you don't have that, here I've got a little bit of code. It's going to take this data about flights in New York City. I'm going to use dplyr. I'm going to group it by date. I'm going to compute the number of flights on each day, and then I'm going to display it with ggplot2. And dplyr uses the pipe, which is really nice, but then we get to ggplot2, and unfortunately, ggplot2 does not use the pipe, so we have to add on this component instead. And this is admittedly like a fairly minor friction, right? But every little bit of friction that gets you out of the flow of data analysis and forces you to think about the language, to think about programming is a bad thing that we want to get rid of. And perhaps even worse is that ggplot2 itself is not internally consistent. Because imagine here I've got a plot, I want to add on some points, and then I want to add on some lines, and then I want to save it. This does not work. If you want to do that in ggplot2, you have to write it in this slightly awkward way where now we've got to put the saving outside the code that creates the plot. As a sort of interesting historical anecdote, ggplot1, or ggplot as it was then known, did not have this problem. So ggplot1 you would create plots like this. So you'd say, I want a plot of the empty cars data, put MPG on the x-axis, weight on the y-axis, and then add points to that, and then save it. And this is valid ggplot1 code. But when I was writing this, I was like, I thought this idea was really elegant, that the way you compose a plot is by composing functions. I thought that was a really elegant idea, but it's really painful to write this code because you've got to write it from the inside out. But the kind of crazy thing is, well, this actually works really well with the pipe. So if I'd discovered the pipe like 10 years earlier, there never would have been a ggplot2. It just would have been ggplot the whole time. And this, in fact, is the plot that ggplot1 creates, which you'll notice is strikingly similar to a ggplot2 plot. Although there are many, 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 many things you can do in ggplot2 that you cannot do in ggplot1. If you do want to play around with ggplot1, I kind of like brought it back to life as a modern R package. It's mainly there for kind of historical interest, but it's kind of fun to play with. Now to illustrate the pipe in a somewhat more realistic context, I want to show you some code from Bob Rudis. And here we're going to use 5 packages: arvis for web scraping, purrr for some functional programming, which we'll talk about very shortly, readr for loading data, dplyr for manipulating data, and lubridate for dates. And we're going to join all of these different packages together in a seamless pipeline. We're going to start by reading some HTML from this mass shootings tracker website. We are going to find all of the HTML nodes that are called A. So A is what you use for a hyperlink in HTML. And they all have a link starting with docs.goo. So these are all links to Google documents. And then we're going to extract that link. And then for each link, I'm going to map over it. I'm going to read the CSV at that link and combine the results into a data frame. Then I am going to turn this date variable into a real date rather than just a string that represents a date, using this mdy function from lubridate that just says the date format is in month, day, year format, and it figures out the rest. And then I'm going to save it into this object called shootings. So I think this is the beauty of the pipe, that you can combine all of these tools from different packages that were not originally designed to work together in this seamless flow. And you can fairly easily, you can at least kind of pick out what are the key verbs here. You might not immediately know what they are, but you can at least identify what are the most important things. This also illustrates something that I have very mixed feelings about, and that is the rightward facing arrow. So you may not know, but R has assignment going in 2 directions. You can assign to the left, or you can assign to the right. I really thought there was no reason you should ever assign to the right. It was just sort of some crazy language feature, but it does look very natural when you come to the end of a pipeline to say, I want to save this to a variable. Personally, I will still never do this, but it's an interesting idea. So that's the idea that when you solve complex problems, a really powerful way is to compose these simple pieces. So all of the packages in the tidyverse, each function individually is quite simple. You can read the documentation, and in 15 or 20 minutes, you can basically understand how that function works. All the pieces are simple, and they have this uniform interface that you combine them all using the pipe. You don't combine some of them with plus and some of them with something else. You always use the pipe to combine them together. And that means now when you go to solve a complex problem, you're not using like some big, complicated off-the-shelf function that is either incredibly complicated or fundamentally limited. What you're going to do is you're going to take you're going to apply one simple function, you're going to advance one little step towards your goal, and because you're taking these little steps, you can easily check your work at each point, and if you discover you've gone in the wrong direction, you just back up a little bit and try again. You want to avoid being in the situation where you kind of take a long journey and then 3 days later you discover, oh shit, I'm in a bad place and I've just wasted the last 3 days of my life. Right? Ideally, you want to take these little steps and check yourself after each step to make sure you're going in the right direction. really, really powerful way of solving hard problems with many pieces. The third strategy that I think is really important is this idea of embracing functional programming. And functional programming, in some ways, is an answer to this question, why are for loops bad? And if you've used R for any amount of time, you will have heard that for loops are bad, and possibly that you're a bad person for using for loops. And this is absolutely not true, and I don't want to like for loop shame you. Like whatever you need to do to solve that problem you have to solve today is a success. If it gets you one step towards your goal, no matter how ugly or inelegant, that's a success. But that said, I think if you do want to advance your skill as an R programmer, learning a little bit about functional programming is really powerful, not because it's going to get you, greater performance or anything, but it's because it's going to allow you to express your ideas with more ease. And I'm going to attempt to explain this, why this is important, with some cupcake recipes. So how many of you made a cupcake from scratch before? So this is a cupcake recipe. This is a cupcake recipe. It is a real cupcake recipe, and I have made cupcakes from it. If you've ever done, so this recipe is great if you've never made cupcakes before because it is very, very explicit, right? It says put the flour, sugar, baking powder, salt, and butter in a freestanding electric mixer with a paddle attachment and beat on slow speed. Or like whisk these things together in a pitcher. Like if you've never done this before, this is great to have this level of detail. But if you've ever made cupcakes before, or you've basically done any type of baking before, this level of detail actually obscures the details. And I think the easiest way to see that is to compare vanilla cupcakes with chocolate cupcakes. So what's the difference between vanilla cupcakes and chocolate cupcakes? So it's cocoa powder, right? The only difference is that in chocolate cupcakes, like this is not the scientific discovery of the century, right? But in chocolate cupcakes, you put cocoa. But because we have all of this repeated stuff, it's very, very difficult to see what's different, right? And once you've mastered one cupcake recipe, that's more important, knowing what's different between this recipe that I already know and this new recipe. Understanding what's different is much more important than seeing what's the same. And this cookbook is basically like 50 pages. There's like 50 recipes, and each recipe like differs by about this amount. And the other reason that's useful to know that is like once you've seen this common pattern, once you've seen 10 cupcake recipes and how they vary, now you can start to say, well, if I want to invent my own type of cupcake, what do I do? What are the knobs I can twiddle? So what I want to do is I'm going to take these recipes, and I'm going to kind of refactor them. I'm going to try and make the difference between these recipes more clear. And the first thing I'm going to do doesn't really have any direct analogy to programming, but it's an amusing story. So I got I was recommended this cookbook by my friend in New Zealand. She said it makes really great cupcakes. I bought it and I tried to make cupcakes out of it, and they just did not turn out very well. I was like, that's really weird. And it wasn't until I went to New Zealand and actually saw her cupcake book, I discovered there were two versions of this book. There's the American version, which uses these ridiculous volume-based measurements, like a scant 3/4 cup of sugar. And then there's the version made for the rest of the world, which uses actual weights. So the first thing I'm going to do with this recipe is I'm just going to convert it to sensible units. The next thing I'm going to do is I'm going to assume a little bit of domain knowledge. So I'm going to assume you kind of if I tell you to mix things together, you're going to figure out the appropriate vessel in which to mix them. And so when I do that, I've tried to preserve a few things that are important, like this is important. You want to mix it until it's sandy, right? That's kind of a good visual cue, so I kept that in. But you can see the instructions are much, much shorter. And I'm going to do one more thing that's going to help make it easier to compare these instructions across recipes, and it's basically I'm going to use variables. I'm going to say, beat together the dry ingredients, that's these guys, and then later on the wet ingredients. And the neat thing, once I've done that, is now I can fit both recipes on a single page, and now you can see precisely how the vanilla cupcakes and the chocolate cupcakes differ. And it's not that I'm adding cocoa, right? It's that I'm replacing flour with cocoa. And I think this is, at some level it's trivial, but at another level this is quite powerful, right? Because it immediately gives you one knob you can tweak. You made those chocolate cupcakes and they weren't chocolatey enough, replace more flour with cocoa. If they're too chocolatey, replace less, right? You now say, well, so maybe you're starting to come up with some theories of cupcakes. And maybe there's some kind of conservation of dry ingredients principle here, right? So how does that apply to programming? Well, again, I want you to take a minute. I want you to look at these two for loops, discuss it with your neighbor. What do these for loops do? How are they the same? How are they different? You've got 1 minute starting now. Okay, time's up. What do both of these for loops do? They're going to summarize every column in this empty cars data frame. What's different? This one is computing the mean, and this one's computing the median. So the problem with for loops is they tend to emphasize the objects that are being manipulated. But often what you're actually interested in is the action. That's the really important difference between these two functions, right? This is just like the cupcake recipes. It's hard to see the difference because we've got so many repeated instructions. And so the idea of functional programming is that it helps us to emphasize the actions. And so this is the equivalent functional programming code compared to these for loops. We're going to use a function that basically that does the for loop for us. So map double is going to take each element in this empty cars data frame, it's going to compute the mean, and it's going to store it in a double or a numeric vector. So functional programming makes it easier to express yourself by increasing your vocabulary. You learn a few new generic verbs, and you can apply them in many situations to solve a very wide class of problems. Now that's kind of the lowest level of functional programming. Things get progressively more and more complicated. From there, I just want to give you two little teasers. So this first teaser does a little bit of simulation. So first of all, I'm going to define a Tibbal that has two columns. The name of a function is parameters. So random uniform, random normal, random Poisson, and their parameters. And then I'm going to use this other function from another functional programming function called invoke map. That's going to take each of these functions. It's going to call runif with these arguments, rnorm with these arguments, and each of these with a common argument. So we're going to perform this simulation with these three different ways of generating random normals, and we're treating these kind of functions and their arguments as data, which is a really, really powerful idea. Another little teaser here, I'm generating a data frame that has some information about the different classes of cars. These are like subcompact, compact, and so on. I'm going to say, well, I'm going to work out a file name based on that. I'm going to work out a list of parameters. And then I'm going to call this R markdown render, where basically I'm going to make a report. I'm going to make one report for each of the different classes of cars, saving each of those reports to a different file name. And here I'm using this function called pwalk that basically walks the arguments in parallel. So you can start pretty simply with functional programming. You can learn a handful of functions that allow you to replace many common for loops with a single function call, which is faster to write because you now have to write like 7 characters instead of all of these. They're less error prone because you're not having to write all this boilerplate every time. And then finally, they help express your code, express yourself better because you can see what's different more clearly. And then as you get better, as you kind of climb this tower of abstraction, you can start thinking more and more about functions and the arguments to functions as data, storing them in data frames, storing them in Tibbals, and then applying functions to them in a variety of different ways. So I wanted to... So a Tribble is just A Tibbal is a transposed Tibbal. So you can see I've just defined it here like I've written the data in rows, basically. Normally when you create a Tibbal or a data frame, you have to write it in columns. This just lets me lay it out a little bit more easily when you're writing a little bit of data inline in your code. So I wanted to finish off by kind of talking about the last thing, which I think is really important. It's a little ill-defined at the moment. I'm still trying to, I believe very strongly that this is true. I don't exactly know what it means, but I wanted to support this with another quote from Hal Abelson. He's a very, very famous computer scientist. But he's saying here, right, that it's only kind of incidental that the program actually runs and does something. The most important thing is that it communicates what it does to other people. And so this kind of acknowledging that code is used by humans, I have kind of three little examples. So again, I don't really know what this means yet, but here are three areas where I think it is important to acknowledge that it's a human using this code. So the first is, these are the kind of the 5 most important functions for the dplyr package for doing data manipulation. Even if you know nothing about dplyr, you know English, or you know some human language. And by using words that are somewhat familiar, they're not exactly right, but they're at least evocative of the meaning, now when you go to use dplyr, you've kind of got a heads up. You've got an extra step forward, because you can kind of guess what some of these things are going to do. And when you learn exactly what they're going to do, it's going to hang in your memory a little bit better, because it's going to hang off some associated concept. Another thing that's important for humans is that humans like to have fun, right? And so I think writing our code should be a little bit playful and a little bit fun. And so here are kind of like 4 package names that are designed to be a little fun. So 4cats, this is like the best package name I've ever come up with, because it is a package for categorical variables. It's also an anagram of factors, and it's a nod to like the cat ladies hashtag on Twitter, a very popular group. Then we've got other things like magrittr. This is a nod to Magritte's famous "This is not a pipe" painting. We've got Tibbals and Tibbals and the troubles with Tibbals. And then lubridate. The goal of lubridate is to make it easy to work with dates and time. So some people find that name a little bit risque. So right, we've got humans. Humans have a language already, and it's useful to reference that. Humans like to have fun. And I think finally with these stickers, a little bit of this is kind of like humans are pack animals, right? It's nice to be able to like identify your clan with people like you just by looking at their laptop and seeing what stickers you have. So these are kind of the things I'm thinking about. They're not very well formed yet, but explicitly acknowledging that it's not just computers, it's not just some mechanical transformation. Like, I want you to have fun when you're doing a data analysis, as much as that's possible. Sometimes that's a lot of fun, right? And sometimes it's hours of pain and suffering. But there should be like some light at the end of the tunnel. So my goal overall is to kind of create this tidyverse where things simply work together. And I've showed you 4 basic principles that I hope help you understand the tidyverse better and you can apply in your own data analysis code. So first of all, sharing data structures. So find this uniform structure that can represent a wide class of problems and use that consistently. Solve complex problems by combining these simple uniform pieces. In R, that the simple pieces are functions, and the way you combine them is with the pipe. I think it's really, really valuable. Never feel bad about using a for loop, but equally, if you learn a little bit about functional programming, you'll find your life gets easier. You won't be able to do anything you couldn't do before, but you'll be able to do things with greater ease and with greater pleasure, and you'll have fewer problems. And then finally, remember, you're not just writing for the computer, you're writing for other people to read. Acknowledge that, remember that. Your code is an artifact of communication, and don't forget that there are going to be other humans reading it. And there's always at least one other human, and that is future you. And future you will often know completely different things to present you, and will be extremely grateful if your code is easy to read and easier to understand. So overall, my goal is to create a pit of success. So this is very different to a pinnacle of success, right? Because you have to strive to get to the peak. You've got to work really hard to get to that pinnacle. The idea of a pit of success is you kind of fall into it without really trying. And so my hope is by making these common components to the tidyverse more explicit and more clear, that you'll just kind of naturally fall into a path of success, a path where, my goal is I want your fingers to be typing R code basically by themselves, while your brain thinks about the specific challenges of your data analysis. And I certainly admit we're a long way from being there today, but that's where I want to go. I want to give you a pit of success where you can easily fall into that. And one of the things that I've been trying to do recently is think not about individual packages, but how to tie them all together. There's a new package called tidyverse. Basically, all the tidyverse package does is help you get all of these packages. So when you install the tidyverse, it installs complete tidyverse. And then when you load it, it loads kind of what I think the most important packages are, the packages that you will use again and again and again in the data analysis. It also gives you some hints about where, for various, probably not very good reasons, I've decided to conflict with existing base functions. So this at least gives you a heads up that dplyr is going to overwrite, filter, and lag from the stats function. So I just wanted to finish with this slide. This gives you kind of a big picture. These are the packages as they are in the tidyverse today, plus a few that I think should exist but don't exist yet. If you would like to learn more about the tidyverse, if you'd like to get better at doing data science or data analysis in R, the place where I've tried to put all of these ideas in writing is this book called R for Data Science. It is freely available on the web. I have just sent the final version off to O'Reilly, and it will be available in print, hopefully, fingers crossed, before Christmas, otherwise early next year. Thank you.